talk, and we're going to talk about hydrolysis, a little bit of amides, as well as pKa's, because pKa's always matter when we're talking about carboxylic acids. And then you previously learned about lactones, and today we're going to talk about lactams. So we just want to remind you what lactones are. So we're going to continue with learning objective 20F, which is the hydrolysis of esters to carboxylic acids. So we're going to do basic conditions today. We did acidic on Friday. We're going to do basic today. And then we're going to talk about amides for the rest of the time. So kind of recapping how we can make amides, lactams, which are cyclic amides, and then hydrolysis of amides. So a lot of amides today. So let us start with our first learning objective, which is really a continuation. It's continued, which is the 4 Ps of nucleophilic acyl substitution from esters to carboxylic acids. Again, we can call that hydrolysis because we are using water or some form of water as our nucleophile. And the whole learning objective is under acidic or basic conditions. And today we're going to be talking about the basic conditions, which is section 20.9. So this hydrolysis reaction under acidic conditions, remember, was the inverse of Fischer esterification. So in basic, it's a little bit different, and it has a different name. I don't know why, but this is often called saponification. I mean, I do know why. It's because it's used to make soap, which is what saponification means. But it is a little bit annoying that they have different names. But if saponification is specifically ester hydrolysis to carboxylic acids under basic conditions. All right, so let's write out our total reaction to make sure we all are on the same page. So again, we're starting with an ester. So we better have that acyl part and the X part, right? So the red is the acyl part. This is our X, our leaving group. So now we're under basic conditions. So instead of water, we're going to use hydroxide. So often it's sodium hydroxide. Right? So this is our base. And unlike the acidic conditions where we had just, we could just use a tiny bit of the acid, right? A catalytic amount of the acid. In this case, this is not catalytic. This is stoichiometric base, and we will see why when we go through the mechanism. Okay, but because it's under NaOH, that is a base that tells you that it's under basic conditions. We don't have to add another base. You often need heat for this reaction. And you end up getting the base version of your carboxylic acid, which is the sodium carboxylate and an alcohol byproduct. Okay, so we know we have to get the carboxylate product because we're under basic conditions, right? If you can't just have a carboxylic acid existing under basic conditions, right? It will immediately get deprotonated because of the low pKa of that carboxylic acid. So that's why we get to that carboxylate. And that is the reason why this reaction is irreversible. We have an irreversible deprotonation at the end of the reaction, which drives it forward. So unlike the acid conditions, which were reversible, right? We're having to bias it either towards the starting material or the product. In this case, it's irreversible because that last deprotonation step drives it forward. It's also the reason why we have to have not catalytic base, because your base is going to get eaten up by deprotonating that last step. All right, so remember, under basic, strongly basic conditions, our organic molecules will have negative charges, not positive charges, okay? It's the opposite to acidic conditions. So we want to be looking for negative charges, and if we see a positive charge, maybe something has gone wrong, okay? So let's talk about the mechanism. Okay, we've got our ester. We've got our sodium hydroxide. So, okay, so we have a strong nucleophile here, right? Negatively charged oxygen, strong nucleophile. Negative charges are fine, so we can just attack straight away. We can do our addition step right away. We pick out our nucleophile. It's going to be one of the lone pairs here. Pick out our electrophile. Better be that carbonyl carbon on the carboxylic acid derivative, always. Nucleophile attacks electrophile, break the weakest bond. So this is our addition step. This carbonyl oxygen now has a negative charge, but that's fine because we're in strong base. Like so. Okay. So again, this OR prime is our X group. It's our leaving group, right? It's not a very good leaving group. It's true. It's not a very good leaving group, but we don't want to make oxygen with positive charges in strong base. So we can do our elimination step right away. This is the step that requires heat. This is why we need heat for this reaction, is because OR minus is a bad leaving group, but it's good enough that if we heat it, we can do it. So we can just do our elimination step directly. Okay, so this is where the heat is necessary. We should reform our carbonyl. We make our carboxylic acid. We have this OR minus. But that OR minus is still very basic, right? And now we have this acidic proton. I think I should draw out the bond to that proton. Right there, right? This is an acidic proton. So that it cannot stop here. That OR minus is going to grab that proton because it's acidic. And this step is irreversible. So this is an irreversible proton transfer. So unlike acidic conditions where all of our proton transfers were reversible, this one is irreversible. So it drives this reaction forward. And then we get our alcohol as our byproduct. And this right here, we are stuck here, which is what makes this reaction not reversible. So that's why when we talked about going from a carboxylic acid to an ester, it was Fischer esterification. That's under acidic conditions only. So you try to do it under basic conditions, it just deprotonates and then you're done. You can't go back. Okay. Questions on that? So we have these two different mechanisms, but overall, it does the same thing, right? Hydrolysis of an ester into a carboxylic acid. And then you either sit at this carboxylate, and then you can add acid at the end for your workup to get your carboxylic acid back. All right, let's do a chime-in question to see if saponification is making sense. All right, which of the following statements is not true about saponification, which is what we just went over, ester hydrolysis under basic conditions? A, in the mechanism, organic molecules tend to have negative charges. B, the overall process is irreversible. C, alcohol is the byproduct. Or D, you need to add a base catalyst in addition to the nucleophile. Feel free to chat with your neighbors. Give you a couple minutes to think about this. Maybe 10 more seconds to get in your answers. All right, let's see what we get. Nice. Okay, excellent. So most people are getting this, right? Basic conditions, it's not a catalyst. You have stoichiometric base, which is your nucleophile. Molecules do tend to have negative charges. That's good. Overall process is irreversible because of that last deprotonation step, and alcohol is the byproduct. Excellent job. Okay, so it seems like we're doing okay with saponification. Any questions on ester hydrolysis before we switch to amides? All right, so let's switch gears a little bit. Learning objective 20G. So this is the 4 Ps of nucleophilic acyl substitution. And it's always the same reaction from a variety of carboxylic acid derivatives to form amides under basic conditions. Which is 20.10. So we've actually already learned 2 of these reactions, but we're going to talk about them a little bit more broadly. Amides are always formed under basic conditions, so that's easy. It's always true. But it must be from a carboxylic acid derivative, not from carboxylic acids. So it can't be from carboxylic acids by themselves, because if we were to do that, right, this is our carboxylic acid. You need to have some sort of amine nucleophile, which is a base. And so instead of doing a nucleophilic acyl substitution, all you would do is acid-base chemistry instead. Okay, so if you mix a carboxylic acid and an amine, you get no amide formation. Because we have that acidic proton, it just pulls off that proton and you're done. Okay, so because amides are always formed under basic conditions, because amines as your nucleophile means that it must be basic conditions, otherwise your base wouldn't be, or your nucleophile wouldn't be a nucleophile anymore. You cannot use carboxylic acids, but you can use any other carboxylic acid derivative. So any carboxylic acid derivative plus an amine will get you an amide. and then HX is your byproduct. So you need at least 2 equivalents of your amine so that one equivalent can act as a base, or you can have 1 equivalent of your amine plus 1 equivalent of a different base. Either is fine. We've actually already seen examples of both. On Friday, I went through both of those examples. And X can equal chlorine, acid chloride, right? We've already talked about that one. It could be this carboxylate to give a anhydride, which we've also already talked about. Today, we'll go through the mechanism of the ester. So those two we showed on Friday. So the ester we'll show in a second. The last thing that I want to mention about this is just reminding ourselves of our nomenclature. So this amine has 2 hydrogens on it. So that means it's a primary amine. And when you do this reaction, you now have 1 hydrogen on your nitrogen. So we get a secondary amide. Right? So we lost a proton as we gained this acyl group. So a primary amine goes to a secondary amide. Similarly, a secondary amine, which starts with 1 hydrogen on your nitrogen, will go to a tertiary amide because we will lose that proton. If you use a tertiary amine, this cannot do this reaction, right? Because we need a proton to lose. So primary amine goes to a secondary amide, secondary amine goes to a tertiary amide. Tertiary amines can't do the reaction because you need to be able to replace a proton with that acyl group. So if you can't do that, reaction can't happen. Okay? Okay. So let's go through the mechanism with esters, because we've already done it with acid chlorides and anhydrides. It's not different. It's not different. Still a nucleophilic acyl substitution. So same mechanism. But let's just talk about the ester to amide version. Okay, so we will start with our ester. So let's say something like this. Okay, we have this amine. In this case, we're going to use the amine as our base as well. So it would need to be an excess. We could add an additional base if we wanted to, but that's fine. So we're under basic conditions. So under basic conditions, negative charges are not a problem. We can do our addition step right away. Nucleophile attacks electrophile, break the weakest bond every time. Addition step to form our tetrahedral intermediate. We should have our X group still attached. We should have our nucleophile attached. We do not want our incoming nucleophile to be positively charged, so we need to lose that proton. So this is where our extra equivalent of our amine comes in, or our base, doesn't matter. We need to quench that positive charge like so. So this is a proton transfer step. So we now still have a tetrahedral intermediate, but our incoming nucleophile is no longer positive. So that's good. Now our counter ion is this ammonium. Oops. Okay. So we're under basic conditions. So O minus is not a good leaving group, but if you heat it and you wait, it will eventually eliminate. So we can do our elimination step directly. Lone pair pushes down to reform the carbonyl, leaving group leaves. This is our elimination step. Again, addition, elimination, the two important steps in this mechanism. So here's our elimination. So we should reform our carbonyl. Now it's attached to our nucleophile. So there's our amide product. And then we lost this alkoxide, and our counterion is still this ammonium. So it's not different. The only thing that changed from the mechanisms we went over on Friday is what this X group is. It's the literal only thing that changed. So they're all the same. They're all the same. They're all the same. Questions? Okay. So that's making amides, right? So we now know we can make amides from acid chlorides, anhydrides, or esters. Let's talk briefly about lactams, which are cyclic amides, which are basically the same, except they're cyclic. But we do want you to be able to recognize them. So learning objective 20H, recognize lactams, which are cyclic amides. And compare their stability to lactones, which is 20.14. All right, so let's remind ourselves what lactones are. We learned about these back in 19.15. So that was a cyclic ester. So we can see here, that is an ester group. Just happens to be in a ring. So that's a lactone. So now we're going to draw the equivalent for an amide. So here is our amide group. It happens to be in a ring. Therefore, it's a lactam. So AM instead of ONE. Lactam is the amide version. And very simply, we've already learned our stability trends for amides versus esters, right? Amides more stable than esters. You can make amides from esters. So it doesn't change when they're in a ring. So our lactams, therefore, are going to be more stable than lactones for the same reasons, right? More double bond contribution, therefore more stable molecule. We will not test you on this, but just for fun and for your knowledge, lactams are actually super important. So if you have a four-membered ring like this, so that's connected to various things. This is called a beta lactam because it has two carbons in the ring. So beta lactams are found in penicillin. So penicillin G, so antibiotics. A lot of antibiotics have beta lactams in it, actually. So this is kind of a really interesting motif that's used in drugs a lot. And so that's one of the reasons why lactams are super important. And then because I'm a polymer person and I like polymers, I also want to show you this one. Make sure I did that right. Alpha, beta, gamma, delta. Yep, epsilon. Okay, so this is epsilon caprolactam. And if you polymerize this lactam, you get nylon. or one version of nylon, right? Like the stretchy kind of sheer fabric, nylon. So nylon is amides, polyamides. So caprolactam is one of the monomers that you can use to make nylon for various textiles and things like that. So lactams are important. That's what I'm trying to say. Lactams are important. We use them all the time. Questions on that? So we want you to be able to compare their stability in the same way that you would an acyclic amide. Okay. All right. So let's talk about hydrolysis of amides now. This one is a little bit weird, but we have the same kind of two mechanisms, whether we're under acidic or basic conditions. That makes it a little bit challenging. So learning objective 20I. So again, we have the 4 Ps of nucleophilic acyl substitution, because they're all the same. From amides to carboxylic acids. So again, we can call this a hydrolysis under acidic and basic conditions. So this is section 20.13. Okay, so we're going to talk about both acidic and basic conditions. Let's just look at the overall reactions, acidic versus basic. So in both cases, we're going to start with an amide. Under acidic conditions, water is going to be our nucleophile. Then we need our acid catalyst. So H2SO4 is a common one. And we will need heat. So this is what tells us that we have acidic conditions, because we have an acid in there. Whereas under basic conditions, we will have our sodium hydroxide. Again, it will not be a catalyst, it will be stoichiometric. But that's the thing that tells us that we're under basic conditions, because that is a base. And again, we will need heat. Under acidic conditions, we end up with the carboxylic acid. And then we'll have an ammonium. So protonated amine at the end, because we're under acidic conditions. We have our carboxylic acid and an ammonium. Under basic conditions, we will have our deprotonated carboxylic acid to make our carboxylate and an amine. Right, so we're sort of, in both cases, we have this additional either protonation or deprotonation at the end that makes them both irreversible. So it's different from ester hydrolysis, where the ester hydrolysis under acidic conditions is reversible. But in this case, neither of them are reversible because of these last proton transfer steps. Okay, so we will get into that as we kind of dig into each mechanism individually. Okay, hopefully that just helps see the overall reactions right next to each other. So let's start with the acid conditions, because the acidic conditions are almost exactly the same as the ester acidic conditions, except for that very last step. Okay, so start with our mechanism for acid. So again, it's not different. We're still talking about a nucleophilic acyl substitution, but we're under acidic conditions, so we're trying to avoid negative charges when possible. Okay. So that means we cannot do our addition step right away. We have to activate our carbonyl or activate our electrophile to make a stronger electrophile first. So this is where our acid catalyst comes in. remember the most basic site is the carbonyl lone pair. So we're gonna protonate like so. So we start with a proton transfer step to make a stronger electrophile. Okay, so now we have a stronger electrophile. So we made our electrophile positively charged. So now it's a stronger electrophile. So now we have positive charges in acidic media. That's good. We're ready to do our addition step. So remember, our nucleophile is water. So the lone pair nucleophile attacks electrophile, break the weakest bond. This is our addition step. Forms our tetrahedral intermediate. Okay, our new nucleophile that just came in is positively charged. We don't want that. So we're gonna have to deprotonate it, right? So we need to lose one of these protons. In addition, N minus is not a leaving group. Like, it will not leave like that. So we also need to protonate our X group here. So again, you can do this in one step or two. So this is our X group, so that's going to be our leaving group, but it's not a leaving group yet. So I'm going to do this in one step just to make it simpler, but you can do this in two steps, no problem. We're just going to grab that proton. This is sort of two proton transfers in one. So we're just trying to get our tetrahedral intermediate into a position to do the elimination step. So one, we don't want our incoming nucleophile to be positive, and we need to make a better leaving group. So that was the purpose of those two proton transfer steps. Okay, so now this whole thing is a leaving group. We can now do our elimination step. So like every other elimination step, our carbonyl oxygen lone pair pushes down, reforms the carbonyl, leaving group leaves. So now we should have our OH group here. We've now generated an amine. Okay, now that we've generated an amine over here, that is a base. So that is going to pull off this very acidic proton over here. And this last step is irreversible. So our irreversible proton transfer happens at the very end, which gives us our final carboxylic acid and our ammonium salt. So I drew these reversible arrows just to show you that all of these steps are technically reversible, but the overall process is irreversible because of this last step, right? Because the pKa difference between these is so large that it's not going to go back. So this last step is really what drives this reaction. So it's not different. I know it's a lot of steps. I know it can look intimidating. It's not different, right? We have our addition step. We have our elimination step. Everything else is proton transfers to get the charges to work out and to prep you for these steps, right? So we can't do addition until we make a stronger electrophile because we're under acidic conditions and this is not a strong enough nucleophile. So we do a proton transfer first. Then we do a couple of proton transfers to make this not positively charged and to make a better leaving group. That's the purpose of those 2 proton transfers. Then we're ready to do our elimination. The final proton transfer is the driving force just because of the pKa differences between our byproduct and this proton. Okay? All the same principles have applied to all of the reactions in this chapter. Questions on the acidic conditions? Okay. Hopefully that one feels a little bit familiar because it's very similar to the ester. The mechanism for the base is also similar, but there's a little bit of an exception alert at one step. So we'll talk about that. All right, so basic mechanism. Again, we're going to start with our amide. Our nucleophile in this case, right, is sodium hydroxide, a much stronger nucleophile. But we do not need to make a stronger electrophile because we already have a strong nucleophile. So we also don't care about negative charges. Negative charges are fine. So we're going to do our addition step right away. Addition step, nucleophile attacks electrophile, break the weakest bond. Every time. Okay, so we did our addition. So under basic conditions, we normally do our elimination right away. Unfortunately, we cannot do that in this case. And that's because this guy right there is such a bad leaving group. It's essentially not a leaving group. You cannot do the elimination right away. It's really hard to break that CN bond. Okay, so that means that in this one instance, we have to protonate it. We have to protonate it. So this is a huge exception alert. Normally, we do not tolerate positive charges in strongly basic media, but in this case, we have to because N minus is just not gonna leave. It's not gonna happen. So we have to protonate it. Unfortunately, we cannot just protonate it first because this guy right here is more basic than our nitrogen. So we actually have to do 2 protonations. The first one is of this negatively charged oxygen just because of pKa's. So if we have water around, this is going to grab one of those. Okay, so this is a proton transfer because of pKa's. There's no reason other than it has to be that way. Okay, then we need to do a second proton transfer from water to make a better leaving group. So this nitrogen now can grab a proton. Make sure that it's coming from water and not acid, because we do not have acid around in basic media, right? So this has to be water. Okay, so this is another proton transfer to make a better leaving group. NR2, and then we protonated this, positively charged. And we have an OH counterion there. Okay, so again, this is unusual, right? We normally do not tolerate these types of positive charges in basic media, but it's a big exception alert. That's only because we need to make this into a leaving group. This is why this type of amide hydrolysis generally takes a lot of time and a lot of heat, because this is not very favorable, okay? But eventually you can get it to go. So now we have a leaving group, so we are ready to do our elimination step, but we can't just push down from the lone pair, because if we do that, we would make a positive charge on this oxygen. And so we call this like an assisted collapse of our tetrahedral intermediate. So our base is actually going to pull off the proton at the same time as we break this oxygen-hydrogen bond, which is going to push down and then push out. So we sort of put the proton transfer all together because we can't make that positive charge on oxygen. So this is our elimination step. So we made our carboxylic acid. We made an amine. We technically made water again. We still have base. Or we can use our amine, which is also a base. Doesn't really matter. But we have base. We have a carboxylic acid, which has an acidic proton. So one of these bases is going to deprotonate our carboxylic acid in an irreversible deprotonation. Again, irreversible proton transfer or irreversible deprotonation at the end. To make our carboxylate. And water is the byproduct. Okay. So this one is weird. This one is kind of the exception to the rule, but it's all driven by the fact that N- is not a leaving group. Okay, so we really need to protonate it in order to make a leaving group. Otherwise, the elimination step is not going to happen. But because we have a more basic site in the molecule, we have to protonate that first. So it does one proton transfer to just because of pKa's, and we do another proton transfer to make a better leaving group. And then the base assisted elimination. Yes? This? That is an ionic bond, right? It's a counterion. So just like every other counterion that we kind of, like, they're kind of loosely associated with one another because they're opposite charges, but they're not like covalently bonded. No. Yes.
I have a question from the acidic.
Yes.
Is the HSO4 never reformed? H2SO4?
Correct, because we have a base in there. Yes. Yep. Because we have that irreversible step at the end. Mm-hmm. Other questions? Yeah. Yep, so here we did do that also, but in acidic conditions, it's normal to have positive charges on our leaving group before it leaves. In basic conditions, it's very much not normal to have a positive charge on it, but we have to because it just won't do it otherwise, right? So I guess the big difference is this first step, right? In the acidic conditions, we got to make a stronger electrophile, whereas in the basic conditions, we already have a stronger nucleophile. So that's kind of like the major difference. Good questions. Any other questions? All right, in the last minute, I just want to sort of emphasize with all of these nucleophilic acyl substitution reactions, one, they're all the same. Two, they're very slight differences, right? And so like, it's okay if you can't just look at it and be like, oh yeah, I 100% know the mechanism immediately, right? It is a problem solving exercise to some extent. And so it's okay to not know the right answer right away, as long as you're thinking about it and can notice when something goes wrong. So for example, if you have an ester and you're doing hydrolysis, right? So we have water as our nucleophile, and say we're doing it under acidic conditions, we have H2SO4 and heat. It's okay if you are just like, oh, I'm not thinking about it, I'm just going to do my addition step right away. So my nucleophile attacks my electrophile, break the weakest bond. And then you draw out what you would get from that. So you would get a tetrahedral intermediate that looks like this. But this is where you need to recognize, hey, I have a negative charge right here. We're in strongly acidic media. This should be a big red flag. So noticing when things go wrong or like when things don't make sense is what you need to be able to do. You don't need to know it ahead of time. You just got to recognize when something goes wrong. So being like, oh, I try my addition right away. Oh, that's a red flag. We're in strong acid. We're not going to make that negative charge. So that means, oh, let me just take a step back and protonate first. So then I would do an alternative over here, right? And have my acid come in. I'm going to protonate it first, like so. And by doing that, I'm making a stronger electrophile, which is also good. So that now, when I try to do my addition step, I am not making that negative charge because we've already protonated it. And so get my color coding off here, like so and like so, right? And so being able to recognize when something goes wrong, right? So recognizing that we have all positive charges, no negative charges. So this is good, right? So we're in strong acid. You want to be checking your charges as you go. So that's part of recognizing sort of the formal charges and Lewis structures kind of as you go. So I'm just trying to emphasize that you don't need to know the answer, like notice it as you go and try to figure out when something goes awry. All right, thank you very much.